Let's take a look at two different ways to find the standard deviation depending on the situation. I'm at wumbo.net where I like to go to find symbols that I can copy and paste or find really good formulas and graphs. What we're focusing on today is standard deviation. You can see there's two different pages. One that has a symbol sigma, and that's for population standard deviation. We can visualize what one standard deviation would look like in a normal distribution. Here we see that it goes from the center, the peaked middle of this curve, over to what we would call the inflection point, which is where the curve flattens out on each side, as opposed to being either convex or concave. That distance, one standard deviation, can be used as a metric and used predictably, as we see down here, to find probabilities with the normal distribution. Depending on the class you're in, you might be looking at that more later, or you might just use standard deviation as a comparison of how widely dispersed or how spread out a data set is in comparison to another, or maybe two groups within a data set. The formula looks kind of complicated. It really isn't too bad. It becomes more and more complicated with bigger and bigger data sets. And that's because we have to do this treatment to each value of the variable, each data point x, that's indexed from 1 to n. So that means all those data points are each going to be reduced by mu, or we find the distance from the mean, some positive and some negative. And the reason why we can't just average that distance is because that would average out to 0. The mean is really right in the perfect middle where all the positives and all the negatives all equal out. Whereas if we square those, we can get rid of all those negatives, look at each as a positive distance, and then also exaggerate outliers or data that are out in the margins. We will have far fewer data there, but they will have a much bigger impact on the standard deviation. Imagine a data point that's 2 from the mean versus 10 from the mean. Obviously, 10 from the mean is 5 times farther away. But if we square each of those, we go to 4 and 100. 100 is 25 times farther away. So we see that exaggeration. The sigma, big sigma here, capitalized, is to add them up. And then we divide by n, just like when we average things out. So there's an average effect here. The square root will reduce it back down to its original units. So the standard deviation is kind of like an average with a second power and square root in there. Now, when we have small samples, we get some bias. We don't tend to observe the most extreme when we take a sample. We'll most commonly sample from that middle bulk of the curve. And so we'll have some bias with our standard deviation measurements of small samples. Therefore, Bessel's correction makes that standard deviation formula dependent on n in a slightly different way. We reduce that n by 1, which will be an effect that's felt a lot more with small samples. Imagining subtracting 1 from a million, proportionally not a huge change, but if you subtract 1 from 5, you're reducing that down by 20%. So a lot bigger effect with small samples for Bessel's correction. It kind of throws a wrench in some of our calculations because most websites will just spit out one standard deviation. For example, Stapplet, we use that a lot in my classes. One quantitative variable single group. For the first part of the video here, I'm going to look at a data set I found on Kaggle, Psychosocial Dimensions of Student Life. This is from an MIT poll of 100 computer science students. So there's our data set. For example, this is a sample. So if I wanted to find maybe just the average age as an initial look into this data set, I can do that like I've done on other problems, pasting those in. I'll just put age here. Just a brief look at this data set. Here's our histogram, average of 22 and a half years old. And we see people varying from 20 to 25. It's a pretty narrow range for these college students. And maybe, a couple years below and above the mean, with a standard deviation coming out to 1.6 there. That for Stapplet is not specified as a population or sample, we're going to assume that it's using the sample formula because that's really what we most commonly are analyzing, our sample data sets. With Stapplet, that's the only thing we're going to be able to find is the sample standard deviation. In Google Sheets, there are many formulas or functions built in, and that's the best place I think you can use to find the population standard deviation. I'm going to zoom in way over here to show you what I'll type. Equals to bring up formulas. And you might even just search the formulas, or some people will go to Insert, Function, and look through there. A lot of options, obviously, but I'll just show you what we need. We need equals STDEV. That's a standard deviation formula. This one has no specification, so we would assume that's for a sample. These first three are older versions. Actually, down here is the new standard for Excel and Google Sheets is stdev.p or .s. And you see that this one just says standard deviation. It doesn't even say sample. That's because the default is sample. Here we have an entire population. And I was back in column A. So I'm going to type A:(A) as my cell reference, and you'll see that entire column light up with the orange box. It is including age, but the formula doesn't look at qualitative responses. It's only looking for quantitative responses. So I can do a quick calculation there. If I need to, I could label it. I would probably say population SD or population standard deviation to write it all out. Now here's the thing, this was just a sample of 100 people, so it really would not apply to this data set. That actually will be false here. The best number to go with will be that 1.561. Let me undo and see what we did get though as a comparison. It's very close, but a lot of times you'll be off in that hundredths place or maybe around the third digit of that measurement. If you wanted to find population standard deviation, that would maybe apply to something like the entire team, or here I've got baseball reference. We could see the batting averages by team for an entire year. And if I was going to find the standard deviation of these types of measurements, then I would want to use a population calculation for that. A great use of standard deviation is if we disaggregate our data by a certain variable or just do side-by-side analysis of one of our quantitative variables. For example, here, if I look at this academic performance column, I can compare people who identified as either average, above average, or below average, and look at something like here, their number of friends that they reported. I use Stapplet, one quantitative variable, multiple groups. And it makes me wonder if these data were actually fabricated for just practice. It does seem interesting to me that we've got 4 people who all said they have one friend there, but it's a great example of demonstrating a standard deviation of 0, where this group had no variation from the mean at all. The second group looks a little bit more like what we would expect over on the left, with a pretty random distribution and a high peak in the middle. We did say 4 people here said they had 0 friends. This mode of 3 stands out from the rest, but then we've randomly got 3 people who said 60 and 4 who said 100. And those groups of people far from the mean are going to drive up the standard deviation to almost 31 for that group with average academic performance. And the highest standard deviation will be in the third group, which doesn't necessarily have the most points. We just see that they're spread out more widely. We don't have really a cluster. We've got 3 students who said 3, 3 students who said 55, and 3 who said 80, which just tend to spread out overall. We quantify that with our standard deviation of 34, the highest variation that we expect from student to student there.